Okay, so we are going to take some notes on 3.2. So this section is about logarithmic functions. And the big idea here, or the most important thing you need to know, is that by definition, a logarithm is the inverse of an exponential. So here's what that looks like. Let's say we have a function f of x, and it is 2 to the x. So it's an exponential function. And if you think about this graph, it would have the ordered pairs 0, 1, and 1, 2. And if we looked at that, it has a horizontal asymptote at the line y equals 0. So 0, 1, 1, 2, so it looks like this. It passes the vertical line test and the horizontal line test, so we know that it's a one-to-one function. Okay, so if we want to talk inverses, when we go to find f inverse, the first thing we are going to do is switch x and y. So we can say x equals 2 to the y. And we have no way of getting y by itself without logarithms. So what you do is you write the logarithmic function base 2, and then the input and output switch places. So here my input was y, so over here my output is y. Here my output was x, now that is my input. And then this is your f inverse, log base 2 of x. So what that means if we think about the graph is that these ordered pairs up here are going to trade places. So when we graph this inverse, the 0 and the 1 move over here, and the 1 and the 2 move over here. And instead of a horizontal asymptote, if y changes to x, so this is now x equals 0, if you think about that line, that would be a vertical line, so that would be your vertical asymptote. And then you'd have the point 1, 0 and 2, 1, and your graph would look like this. So logarithmic functions have vertical asymptotes. They contain the point 1, 0, and then your base and 1. And that means that their domain is not all real numbers like exponentials. So their domain is going to be greater than 0, or wherever that vertical asymptote has shifted to. The flip side of that is that the range will be all reals, because that it was your domain of exponentials. So here my domain is all reals, here my range is all reals. Here my domain would be greater than 0, here my range is greater than 0. So your domain and range and everything switch there as you go. Okay, we'll look at some more graphs in a couple minutes, but one thing I want you to practice first is just rewriting. So in order to really understand exponentials and logs, you should be able to rewrite from one version to the next. So if you saw something that said the log base 4 of 1 over 1,000 equals -3, you have a logarithm, so if we rewrite it as an exponential, so you're rewriting between logs and exponentials, inverses of each other. Whatever your base is stays the same. And then this was my input, so now it's my output. This was my output, so now it's my input. In exponential form, you should be able to do the math. Oh, sorry, I wrote the wrong base. This is base 10. My bad. Sorry, that's base 10. So then you can see 10 to the -3rd. The negative puts it in the denominator. 10 cubed, you would have 3 zeros, so you can see how that rearranges. Okay? If we go the other way, so if we had said 9 to the 3/2 equals 27. So before we rewrite, let me remind you about this because you'll have to deal with that. This is like saying the square root of 9 cubed. So the 3 stays the exponent and that denominator goes inside the rational. So the square root of 9 would be 3 cubed, which is 27. So just a reminder about those because that will pop up. If we rewrite this now, when you rewrite that as a logarithm, the base on your exponential is the base on your log. So this is base 9. And then the input and output trade places. So now the 27 is my input and the 3/2 is my output. Okay, so that's how you rewrite them. Know that if you have a natural log, so if we had started with the natural log of 4, and we knew that was about 1.386, I would say we typically round to 3 decimals, and I think WebAssign will say the same thing. So if we have this, then remember natural log is log base e. So when I rewrite this, I might have an exponential with a base e, and then I have the 1.386, and that equals about 4 if you check that in your calculator. Okay, so that's how we rewrite them. And rewriting is important because it helps us evaluate things without a calculator. So if your directions on WebAssign say evaluate without a calculator, that's what you need to be practicing, because on the test it'll be written so that you practice this without a calculator. Okay, so if it says evaluate without a calculator, so if we practice an easy one first, if it says like the log base 4 of 16, and you're evaluating that, I typically put like a question mark or something here so that when I rewrite, I am thinking my base is 4, I don't know my exponent, but it needs to equal 16. So then what does your exponent have to be? It has to be 2. So log base 4 of 16 equals 2. Let's try another one. Let's say that we have the log base 3 of 1/9. So if I put my question mark in here, I'm thinking 3 to what power is 1/9? So remember, a negative exponent is what's going to flip it to the bottom, so I know it needs to be negative, and then 3 squared is 9, so my answer is -2. The negative would flip it to the bottom and then make the 9. Let's look at another. What if we had the log base 3 of the square root of 3? So what you need to think about here, when you rewrite, you're thinking 3 to what power is the square root of 3? Well, this is really a 2 in my rational, so that's like saying 3 to the 1/2. So my exponent is 1/2. So remember that a 1/2 exponent is a square root. A 1/3 exponent would be a cube root. So whatever's in the denominator goes inside the radical. Okay? What if we had said the log base 5 of 1? So we're trying to figure out what that equals. So we'll think of 5 to some exponent is 1. What's the only exponent that can be here to give you a 1? 0. Anything to the 0 power is going to be 1. So that is a couple options for evaluating without a calculator. You should also be able to evaluate with a calculator. So if it asks you for log and there's no little base, that's log base 10. That's the button on your calculator that says log. If it says ln, that's natural log, and that's the button on your calculator that says ln. So you can use either of those to check on your calculator. The last thing I want to look at then before we graph is just a couple basic properties. And sometimes these are called inverse properties because logs and exponents are inverses of each other. So it's based on that idea that exponents and inverses are going to undo each other. So if you're asked to simplify, and you have something like the log base 3 of 3 to the 2x. So my base here is 3, my base here is 3. So that's important to notice, that the base on your log and the base on your exponent are the same if we're going to use the property. Before using the property, I want you to understand how we rewrite this. So if I rewrite this, I had a log, I'm now writing an exponential. I write my exponential, 3 is my base. I don't know what my exponent is, and then I have 3 to the 2x. So what does that question mark have to be? It has to be 2x. So once you are comfortable with rewriting, the property says logs and exponents are inverses of each other. So think about this. If I have x plus 2, the inverse operation would be minus 2. What happens when you add 2 and you subtract 2? They cancel and you just have x. So what happens when I have the log base 3 and an exponent base 3? The logarithmic function and the exponential function undo each other, so this cancels out, and I'm just left with the 2x. It works similarly if you're starting with an exponential. So let's say I have an exponential that's a 7, and then up in the exponent it says log base 7 of 5. So if you're thinking inverses, what I want you to recognize first is that you have an exponential with a base 7 and a logarithm base 7. Those two functions are inverses because their bases are the same, so they cancel out. So you should get 5. The easiest way to see that is to practice the rewriting. So if I'm thinking about how I would evaluate this without a calculator, I can rewrite from an exponential to a log. So I would say log, my base is 7, of my output equals my exponential. So what does the question mark have to be? It has to be 5. This log cancels with this exponent, and you just are left with the 5. Okay? And then the last property just says this: if you have the log on one side and the log on the other side, you can cancel those out. So if we have something that looks like, let's say, log base 3 of 5 equals log base 3 of 10x, because this is log base 3 and this is log base 3, they cancel each other out. These inputs have to be the same. So if I know that 5 equals 10x, I can divide the 10 over and find out that x is a half. So those are some properties you will see. These are inverse properties, and this is just a property that says when I have the same logarithm on each side, my inputs have to be the same. So you'll do some simplifying without a calculator. You'll do some simplifying with a calculator. Any word problems you see would be calculator-based, where you're just substituting, typing it in your calculator, and going from there. So then the last thing I want to deal with or practice here is a couple examples of graphing. And we will do some more of this together in a couple days. But to start with, you need to understand your exponent graph first. So let's say the problem that you are given is asking you to graph the function log base 4 of x plus 1 minus 7. So the first thing you need to understand is your parent function. So I would say that my parent function is, hold on, I'm going to call this g of x. My parent function, f of x, would just be log base 4 of x. Remember, parent functions have no transformation. So I remove the plus 1 and I remove the minus 7. So if I can graph this, then I need to just go 1 to the left and down 7. In order to graph this, I need to think about its inverse. And its inverse would be 4 to the x. So I want to start with that. I want to start with this 4 to the x. So remember, with exponentials, you have 0 and 1. When you plug in 0, you get 1. When you plug in 1, you get 4. Then in order to get my parent function table, f of x, I need to put the 0 and 1 on this side and the 1 and the 4 on this side. So my x and y's trade places. Okay? If this is my parent function table, that's the table I transform. So if I know that I need to go left 1 and down 7, then I can go left 1 and down 7. So I have these ordered pairs, 1, 2, 3, 4, 5, 6, 7, and 3, negative 6. The other thing you need to know is that exponential functions have a horizontal asymptote at 0. Logarithm functions have a vertical asymptote at 0. But if my vertical asymptote starts at 0, then I need to think transformations. If I go 1 to the left, my asymptote just moved. And then going down 7 doesn't move anything. But my asymptote moved 1 to the left. So I have an asymptote there. Drawing that asymptote is super important because that lets you see which way to draw this curve. Remember, it's going to like hug into the asymptote and then go away the other direction. So in this case, I could say that my domain is -1 to infinity with parentheses. I don't actually equal -1. Your range is all reals, -infinity to infinity. If you needed a y-intercept, it might ask you that in your homework. Then we can see that at 0, -7. If you needed an x-intercept, we don't necessarily know how to solve these equations yet, so you would be setting your equation equal to 0, moving the 7 and doing some rewriting or some inverse operations. We'll do that towards the end of the week probably, so we're not quite there yet. But those couple pieces you can see. Sometimes you'll be able to see the x-intercept on the graph, and if you have the ordered pair from your transformations, you should be able to use that as well. Okay, so let's do another one. Let's say that we have the function, h of x equals 2 plus the log base 2 of -x. So we need to think about our parent function first. Our parent function, f of x, would be log base 2 of x. So then we think about its inverse. Its inverse would be the exponential function 2 to the x. So if I make my inverse table, I have 0, 1, 1, 2. If I plug in 0, I get 1. If I plug in 1, I get 2. When I do my regular f, my parent function, my y values become x values, and my x values become y values. After x and y trade places, we do our transformations. So this says I'm going 2 up, and I'm flipping my x values. So my x values become negative, and my y values go up 2. So negative 1, 2, and negative 2, 3. You typically have that vertical asymptote at x equals 0. If I'm going up and down, it hasn't moved. And if I flip or multiply by a negative, it hasn't moved. So I have this vertical asymptote here at the y-axis. If your graph flipped over, it should make sense that I'm now over here curving that way. So now your domain would be negative infinity to 0. Range is still all reals. This time we don't have a y-intercept, and to find the x-intercept, you'd have to do some algebra. All right, let's look at one more. So if our last function, h of x, says, we're going to go negative 3 times the log base 5 of x minus 4. So remember your parent function, when you remove all transformations, my parent function would just be log base 5 of x. So when I start out, I'm thinking about the exponential, I'm thinking about the inverse. In exponential functions, you plug in 0 and 1, but I put those in as y values. You'll see that on your worksheet. So when you look at the 3.2 worksheet, the 0 and 1 are filled in as y values instead, because I've thought through the inverse, which is the exponential. But since we're doing inverses, they flipped to y values instead. When you plug in 0, you get 1. When you plug in 1, you get your base. So that base 5 is where that's coming from. After that, we do our transformations. So we know that the 4 is sending us right 4. So if I go 4 to the right, I'm at 5 and 9. And the negative 3 is outside the function, so that's a vertical stretch by negative 3. Or you could say it's also a vertical flip, or that you're multiplying your y values by negative 3. So when I graph these points, I have 5, 0, and 9, negative 3. And then if you think through your asymptote, our vertical asymptote starts at 0. If I go 4 to the right, it goes 4 to the right. And then because I had a vertical flip, everything flipped this way. And then it stretched out as well. So I'm coming down here and going that way. You can kind of see how you would have like a line between these 2 points, and then just like sneak in there by the asymptote and finish your curve. So your homework is to do both the 3.2 WebAssign and the graphing worksheet. And all of that needs to be done when I see you next. So get a start on that, and hopefully that goes okay.